Hi everyone, welcome back to my channel. In this video, we're going to talk about one of the most important and most misunderstood concepts in machine learning. If I tell you my AI model is 93% accurate, would you trust it? Today, I'm going to show you why that number can be dangerously misleading, especially when your data is imbalanced. We'll break down what accuracy actually hides. Look inside the confusion matrix and see where models really succeed and where they fail. Then I'll explain precision and recall in a simple, intuitive way, and show you how changing the decision threshold forces a trade-off between them. By the end of this video, you'll know exactly why high accuracy doesn't always mean a good model, and how to evaluate machine learning systems the right way. Are you ready? Let's go.
Let's imagine the system is trained to look at 60,000 handwritten images and decide whether each image is the number 5 or not. So this is a binary classification problem. For every image, the model answers a simple question. Is this a 5? Yes or no? Now here's the twist. Suppose this system is programmed with a completely wrong strategy. It always predicts not 5, no matter what image it sees. What happens then? Out of those 60,000 images, only 6,000 are actually the number 5. The remaining 54,000 images are not 5. Because the model always says not 5, it correctly classifies all 54,000 non-5 images. But it fails on all 6,000 images that really are 5. So the accuracy becomes 54,000 correct predictions divided by 60,000 total images. That gives us an accuracy of 90%. And this is the problem. How can such a useless system achieve 90% accuracy? The issue comes from the data itself. Our dataset is imbalanced. Only 1 out of every 10 images is a 5. This is exactly what we call an imbalanced dataset. And in such cases, we often fall into something known as the accuracy trap. The accuracy trap means that accuracy alone is not a reliable metric for judging how good a model really is.
Now let's clarify some important terms. In classification problems, we call the class we care about the positive class. In this example, images of the number 5 are positive. In other problems, positives could be cancer tumors, fraudulent transactions, or spam emails. Positive simply means this is what we are looking for. So what is a false positive? A false positive happens when the model predicts positive, but the sample is actually negative. For example, diagnosing a healthy patient as having cancer, flagging a normal transaction as fraud, or marking a legitimate email as spam. Now, what about a false negative? A false negative is the opposite. It happens when the model predicts negative, but the sample is actually positive. That means a real cancer tumor is missed, a fraudulent transaction goes undetected, or a spam email slips into the inbox. False always means wrong. Positive and negative describe whether the case is something we care about. Understanding these mistakes is critical because accuracy alone completely hides them.
So positive means correctly identifying the thing we are looking for, and negative means identifying that something is not what we want. False simply means an incorrect decision. Therefore, false negative means incorrectly deciding that a case is not what we are looking for. In other words, the item was actually positive, but the model failed to detect it. And false positive means the model incorrectly decides that a case is what we are looking for, even though it actually is not. So as we can see, false positives and false negatives are key concepts in machine learning, and increasing either one of them can lead to serious consequences for a system. Let's look at these images to make this clearer. In the first example, we see a security screening scenario. On the left, a false positive occurs. A harmless object such as a piece of metal is incorrectly detected as a weapon, causing unnecessary delays and trouble for an innocent person. On the right, we see a false negative. A real weapon is not detected, allowing a dangerous individual to pass through security unnoticed. In the second example, we look at pedestrian detection in self-driving cars. On the left, a false positive happens when a shadow is mistaken for a human, causing the vehicle to brake suddenly for no real reason. On the right, a false negative occurs when the system fails to detect an actual pedestrian, leading to a dangerous accident. In the third example, we see a financial fraud detection system. On the left, a false positive flags a legitimate transaction as fraud, blocking a customer's card and creating unnecessary stress. On the right, a false negative allows a fraudulent transaction to go through, resulting in real financial loss. In the final example, we look at medical diagnoses. On the left, a false positive leads to unnecessary chemotherapy for a patient who does not actually have cancer. On the right, a false negative misses a real cancer diagnosis, resulting in a failure to treat the disease in time. These examples show why false positives and false negatives matter. Accuracy alone cannot tell this story. To build truly reliable systems, we must carefully balance these errors depending on the real-world consequences. Now let's go back to our example and calculate the confusion matrix for it. A confusion matrix splits all the predictions into 4 simple buckets. You've got your true negatives. These are things that weren't a 5, and the model correctly said they weren't. Then you have true positives. These were actual 5 south, and the model correctly found them. Awesome. The other 2 boxes, though, that's where the mistakes are. False positives are when the model cried 5, but it was wrong. And false negatives are the actual 5s that the model just completely missed. Okay, so let's plug in the numbers. It got over 53,000 non-5s, right? Great. And it found over 4,000 real 5s. Also great. So the accuracy becomes, as can be seen in the picture, 93%. But look at the errors. It incorrectly flagged over 1,500 images as a 5 when they weren't. And maybe even worse, it completely failed to see over 1,300 images that actually were 5s. All of a sudden, that shiny 93% accuracy score starts to look a little tarnished, doesn't it? This is exactly where accuracy becomes insufficient, and we need to move beyond it to evaluate our models properly. Accuracy alone cannot capture the weaknesses of a model. Particularly, it is unable to highlight the 2 important numbers we've just learned: false positives and false negatives. Therefore, we must consider alternative evaluation metrics that explicitly reveal these types of errors. The key question then becomes, which metrics can effectively expose and quantify these weaknesses?
Let's look at precision and recall. They give a much richer picture of performance than simple accuracy. First, precision. It's the quality of predictions. When the model says yes, how often is it right? High precision means you can trust it. Next is recall. This is about completeness. Of all the things out there to find, how many did the model catch? High recall means you're not missing much. So precision minimizes false alarms, while recall minimizes missed opportunities. They are competing goals. There's almost always a trade-off. You rarely get a perfect score on both. It's like a seesaw.
First, let's see what precision is. Think of this as the quality of the model's positive predictions. It answers a simple question. Of all the times my model flagged something, how often was it right? So a high precision means that when the model says yes, you can probably trust it. And on the other side of the coin, you've got recall. This isn't about quality. It's about completeness or quantity. Recall asks, of all the positive things that were actually out there to find, how many did my model manage to catch? High recall means your model is a great detective and doesn't let much slip by. Back to our example. Let's calculate precision. And when we do the math for our model, the precision is only 72.9%. So think about that. When our model gets excited and shouts, "I found a 5," it's wrong almost 30% of the time. Yep, that's a huge drop from that 93% we were so excited about. Now, the other side of this coin is recall. The recall is 75.6%. Recall asks a different question. Of all the 5s that were actually in the data, how many of them did our model manage to find? This means we're straight up missing almost a quarter of all the 5s we were looking for. But the problem is that we cannot make both precision and recall high at the same time. When one increases, the other typically decreases, and vice versa, like a seesaw.
Yeah, it's kind of like a seesaw. If you try to make your model more precise, meaning you make it super cautious about flagging anything, it's probably going to miss a few things and your recall will go down. And if you tell it, "I want you to find everything," raising your recall, it's going to get a little trigger happy and start producing more false alarms, which hurts your precision.
To get why, let's just quickly peek under the hood. The model doesn't just give a simple yes or no. It gives each image a score. If that score is above some line we've drawn in the sand, our decision threshold, it calls it a 5. If it's below, it calls it not 5. And where we decide to draw that line changes everything. And you can probably see where this is going, right? We can move that threshold. If we make the model more strict, raising the bar, we'll get fewer false alarms, which means our precision goes up. But we'll also start missing more of the real 5s, so our recall goes down. And if we lower the bar to catch more 5s, our recall goes up. But we'll start getting more false alarms, and our precision takes a hit.
And this graph just makes it crystal clear. Look at that. As we move that decision threshold, you can see the recall line and the precision line literally move in opposite directions. As one goes up, the other goes down. They're like two ends of a seesaw.
In Python, when we use the predict method, the model applies a fixed decision threshold of 0.5 by default. What does this mean? For probabilistic classifiers such as logistic regression, the model first computes a probability for the positive class. If the predicted probability is greater than or equal to 0.5, the sample is classified as positive. If it is less than 0.5, the sample is classified as negative. This behavior is hard-coded inside the predict function. If we want to change the threshold, we should replace the predict function with the function shown in figures. By doing this, the threshold changes from 0.5 to 0.35.
So what do? Which one should you aim for? Well, the answer totally depends on what you're trying to accomplish. There's no such thing as a best model in a vacuum. There's only the best model for a specific job. Say you're building a filter to make sure videos are safe for kids. You need incredibly high precision. You'd rather block 100 good cartoons by accident than make that one critical error. But now, imagine you're building a system to detect shoplifters in a store. Here, you want really high recall. The goal is to catch as many potential thieves as possible. You're okay with a few false alarms. Deciding where to set that balance isn't just some nerdy technical detail. It's a fundamental product decision. It defines what you want your AI to actually do in the real world and what kinds of mistakes you're willing to live with. So if it's a constant balancing act, is there a way to roll both of these vital signs into one single number to give us a balanced report? You bet there is, and it's called the F1 score. The F1 score is what's known as the harmonic mean of precision and recall. Now, harmonic mean sounds a little complicated, but the key idea is that it gives a much better sense of balance than a simple average. It heavily punishes a model if either precision or recall is really low. This makes it a fantastic single metric to judge a model's performance, especially for those tricky, imbalanced datasets we started with. Thank you for staying with me all the way to the end. We started with simple accuracy, moved on to the confusion matrix, explored the tug-of-war between precision and recall, and finally reached the F1 score, which tries to balance them both. So from now on, if a colleague ever says, "Our goal is 99% precision," you now know the smartest possible question to ask. Okay, but at what recall? Knowing to ask that question is how you start building AI systems that aren't just accurate on paper, but truly useful in the real world. If you found this video helpful, please support me by sharing it with your friends and anyone who loves AI and machine learning. Don't forget to subscribe to the channel, and feel free to share your thoughts and ideas in the comments. I'd love to hear from you.